from the deep sea water. There are many other spin-offs from this utilization of deep sea water of the OTEC plants. So today we are very fortunate. We're going to have 6 leading speakers to be led first by Professor Yasuyuki Ikegami. I will introduce him first. Then I will introduce the other 5 speakers one by one. Now, Professor Yasuyuki Ikegami needs no introduction. I must say I met him for the first time exactly 10 years ago in February in Malacca, when both of us were at the International Oceanographic Commission Western Pacific Countries Workshop on Marine Renewable Energy. And that's the first time we met, and we've been working together since then. And I think one of the highlights of today is a result of our long-time association and also partnership. So I'm very happy. And Professor Yasuyuki Ikegami also is a student of a very famous nuclear engineering professor, Professor Uehara. So we have a very good person with us to lead this program, and he's now has been the director of the Institute of Ocean Energy, Saga University in Saga, Kyushu Island in Japan. He's very well known throughout the world. So you just Google Ikegami, his name will pop up. So those of you know him for the first time, please do that. Now, I have the honor and pleasure now to invite Professor Yasuyuki Ikegami to make his presentation, introduction and presentation. Thank you very much, Professor Yasu. The floor is yours.
Thank you very much, Dr. Abu-san. Yeah, we have over 10 years history to realize and promoting the implementation of OTEC in Malaysia. So as Dr. Abu-san introduced me, so I would like to explain briefly our SATREPS as a research project director in this program. Yeah, so this SATREPS project development of advanced hybrid ocean thermal energy conversion technology for low carbon society and sustainable energy system, first experimental plant of the Malaysia. So this project term from the April 2019, 5-year term project. So our overall goal, implementation of the combination of the hybrid OTEC and deep sea oil applications, so-called Malaysia model commenced in Malaysia. So this project is promoting hybrid OTEC. Hybrid OTEC, so we both produce electricity and desalinated water, new system. So under this project, very important realize the Malaysia model refers the Kumejima model. Kumejima model is very famous deep sea oil application society in the world. So Dr. Abu-san evaluated Malaysia has a huge potential of the OTEC. So we want to realize the HOTEC. So OTEC part and the desalination part as one system. So this heat exchanger is very key technologies. So we will develop and realize this hybrid OTEC system. So in this project, so this transfers from the Japanese achievement Saga University facilities and Kumejima. So we transfer the our equipment and the technology and the knowledge. So finally, we want to promote the social implementation of the 1 mega to 10 mega OTEC system in Malaysia. So this project structure chart is Japan side and Malaysia side. Japan side, Saga University, Tokyo University, and ICE, and private sector Genesis. And the UTM side, Malaysia side, UTM is a leader, and UPM, UN, UKM, UMT as a private sector infra commerce. So we are signing the both vice president UTM and Saga University is a big success ceremony is a signing. So we have 5 output. One output is a pilot plant development to output to the optimum conditions and operation. Third is a sustainable combination of the deep sea or multi-use in Malaysia using hybrid OTEC is established. Fourth, effect of the environment and the CO2 emission is clarified. 5 is a human capital on the OTEC technology and business in developed. So this project is with a matching foundation supported by Malaysia MOHE. So unfortunately, under the COVID-19, OTEC building is delayed. So we want to construct the pilot plant in next fiscal year, 2020, October or November. So then we will test it. So now already constructed the HOTEC in Japan. After the heat balance, some tests designed, now already pre-assembled in Japan. So after that, we want this year, we will transfer this facility from Japan to Malaysia. So already designed the UPM, UTM OTEC Center. This project leader is Dr. Kairi. So until this year, end of this year, we want to transfer this HOTEC system. So and we have promoting human capital development. So 2 years ago, before the COVID-19, weekend trainings, on-site training. 10 young researchers attended this program. So, but unfortunately, from this year and from the last year and this year, we will online training. So about 17 young researchers training using our Saga University facilities and Kumejima facilities. Live tour we organized. So last week we 2 days program already finished. From the next week, day 3rd, 4th, we will now planning. So this second SATREPS forum, we are very happy to hold this forum. So in this forum, so keynote lecture, this SATREPS project manager, Dr. Satya, she will present all our SATREPS project and OTEC technology and the Malaysia marine renewable energy in Malaysia. Please join and enjoy this forum. Thank you for attention. Abu-san, please.
Yes, thank you very much.
So sorry, very short presentation. Yeah.
So very excellent. Thank you very much, Professor Yasu, for your very short but very concise presentation on our SATREPS OTEC program within the since 2019, and we're going to complete this hopefully by 2024. But because of COVID, we have to extend this program to another year. So our first speaker This morning, I have the honor and pleasure to introduce my colleague, technologist, Dr. Satya Bama through Ghana, and she's the third director of UTM Ocean Thermal Energy Center, and she is a senior lecturer in Razak Faculty of Technology and Informatics of UTM, and she's registered with the Board of Engineers Malaysia and member of other institutions, including Institution of Engineers Malaysia, Energy Institute of UK and Malaysia. Currently, she is focused on ocean thermal energy conversion and its efficient technology to tackle sustainable development goals and 2050 decarbonization actions plans with oil and gas industries. In addition, she's the project manager for SATREPS project 2019 to 2024 and could be extended to 2025. And she received a PhD in electronics engineering, focused on thin film solar cells from Waseda University of Japan in 2015. She has vast experience in development and application of efficient materials for solar cell photovoltaic systems. Upon joining UTM, she has been actively involved in the STEM education initiatives and programs as part of university social responsibilities. Above all, for the past 18 years, Dr. Satya has involved herself in design, development, analysis, lead trainer, and managing various electrical and electronic testers, telecommunication, renewable energy industries in and out of Malaysia. So without much ado now, I have the honor and pleasure to invite Dr. Satya to make your presentation. Thank you. Dr. Satya, you have the floor now.
Thank you very much, Dato. Can you hear me?
Yes, very clear.
Okay, good. Thank you very much, Dato, for the overwhelming introduction. Allow me to share my slides. I hope that everyone can see my slides.
Quite clear here.
Okay, thank you, Dato. A very good morning, ladies and gentlemen. This is our second SATREPS OTEC forum. And my title for today is going to be OTEC Technology as a Marine Renewable Energy in Malaysia. Precisely with the guidance of Dato Baka and also Prof. Ikegami and also the rest of the team in UTM OTEC, we would really like to materialize and move forward. How can we bring in such renewable energy, the OTEC, into Malaysia? So the main idea and the focus we put forward is precisely to bring in the benefit and also a spin-off and so on. Here, these are my the team members who have directly or indirectly contributed to the content of today's presentation. The outline of my talk for today is starting off with the marine. What is marine renewable energies? The definition a little bit. And then moving on to OTEC and the difference in the HOTEC, the hybrid OTEC system, and followed by the OTEC potential in Malaysia, touch base on some of the SEDA's way forward or their vision for Malaysia and so on. And how can we commercialize OTEC plant, let's say 10 megawatt, and the way forward, how we could hand in hand move forward the subject matter for the nation and the people in the world. So this is to highlight and the definition of marine renewable energies by the OES, Ocean Energy Systems, whereby it is the technology collaboration program by the IEA, which is under the United Nations. So if we look at this, there are they have defined and highlighted 4 main technologies and systems for as the renewable energy, a marine renewable energy, which is the tidal and currents, the ocean thermal energy, which is our subject matter for today, the salinity gradient, and the waves. You may think why offshore wind is not here, or, when we talk about marine renewable energies, as the image here focuses and pinpoints that it has to use the ocean as the medium. So thus, wind offshore on land is above the in the air. You see, it's not utilizing the ocean waters as the medium. So that brings us to the next. What are the OTEC demo plants that's available currently, already built, developed, and is been tested, running in the world? So the first one here, we would like to highlight. In the 2013, the Okinawa in Kumejima, they've confirmed and validated this 100 kilowatt of an OTEC on-land OTEC plant, followed by the 2015 in the Hawaii by the Makai Engineering for 105 kilowatt. This is also an on-land OTEC plant. So to date, these are the two on-land OTEC plants that's standing high in Okinawa, Japan, and in Hawaii. So then, in 2021, by the professor, Dr. Kim, of the Koreans, the CRISO, they have built the floating type OTEC, and the size or the capacity of a 1 megawatt floating type OTEC, and it was planned to bring it to the Polynesian or Micronesian islands there, Kiribati, and to confirm the 1 megawatt. However, due to the pandemic, there were certain delays and so on. And to date, if I'm not mistaken, the highest that's been confirmed using this floating type in the ocean, the Korean oceans, is about 350 kilowatt or so. So we hope that and wish Prof. Kim will be able to confirm this 1 megawatt at the Kiribati soon. So then moving on to some other studies that's happening under the CTCN, this Ocean Energy Technical Pre-Feasibility Study has been confirmed to be put up or set up in the Nauru by the Japanese Tokyo Electric Power. This was really done way back in 1981. However, due to certain reasons and challenges, it was put on hold. And now they have restarted, and Prof. Ikegami and team, they have also involved and also presented the report on the feasibility study. Then moving on with another plan in Japan by the Ministry of Defense, support securing the budget for a new installation of the deep ocean waters. So this is planned for the Kumejima town to enlarge from 100 kilowatt to 1 megawatt of OTEC. So this simply defines and highlighting and giving us a very strong message that OTEC has got the potential and its benefits are really overwhelming. So with that, in a very quick and simple way as possible, this is the principle of OTEC, the closed cycle OTEC system, whereby it uses a temperature difference of 20 to 25 degrees C, and the working fluid for that temperature is ammonia. To date, that's been the efficient working fluid, and OTEC can supply us with stable power supply 24/7. This is one of the important point that we would really like to emphasize. And the system, the closed cycle system, will be utilizing the deep ocean waters on the at the condensation process, and the surface seawater for the evaporation process. And the working fluid ammonia is being evaporated, change phase into vapor gas, and goes to the turbine, turns the turbine and generates electricity. And it comes back to the condenser part, and working fluid is condensed, and the liquid of the ammonia circulates. So the working fluid circulates in the system. So in a simple manner, this is the principle of OTEC. And of course, one may think, what about having different working fluid and so on. For this 20 to 25 degrees C of a temperature gradient to date, as I mentioned earlier, ammonia has been the efficient. So let's say if we have a different temperature gradient, higher maybe 60 degrees C or so, then we will be, we have to select further new working fluids for to materialize the OTEC system. Then I did mention about OTEC and its spin-offs. So that is also loads of benefits whereby an OTEC plant can combat the energy issues, the access to clean water, the food supplies, rare earths mining. SWAC is another system that seawater air conditioning, and this can be utilized. Dato Baka is anchoring this and trying to highlight in Malaysia we can utilize this for the data center cooling and so on. Yeah. So, but this as a practice is already there in other parts of the world. So it's a matter of how do we make the benefits of OTEC for Malaysia model itself, and many more to explore. So this is to highlight the benefits of OTEC. And when I say the food supplies, it's very much focused on the aquaculture, cool greenhouse plants, and so on. Yeah. That brings us to the current project that we are focusing, which was already mentioned by Prof. Ikegami and Dr. Baka just now. So under the project, Science and Technology Research Partnership for Sustainable Development. So it's called the SATREPS program, which is funded by the JICA JS3 and Malaysian Ministry of Education, Higher Education. And IOES and UTM is the leader of the program, supported in Japan by Tokyo University and ICE. And we have the industry players. On the Japanese side is the Genesis Incorporation, and on Malaysian side is the Infracommerce. Of course, in Malaysia, many industries and companies are showing interest, and this will grow. We hope that it will grow further in order to really maximize the benefits of OTEC. And in Malaysia, we have a huge consortium of universities involved in this project. Now, after seeing the conventional closed cycle OTEC system, now it brings us to the hybrid OTEC design, which is the core component of the SATREPS project. So because SATREPS project, there has to be technological novelty, then only one can secure the project. So here, the technological novelty, comparing with the conventional OTEC system that has put forward, is the hybrid heat exchanger, or also known as EVACON, evaporator condenser, which will be shared by Dr. Yasunaga later, most probably. And also the flash chamber, which is playing a role in the desalination of the water. In a nutshell, it's a combination of the open cycle, and this open cycle is for the production of the desalination water, and we are using the surface sea water for the desalination part in this project. And the closed cycle, as the conventional one, is for the power generation or electricity generation. So that being said, we hope upon confirming the actual results of the OTEC, it will be the most advanced OTEC system in the world. So this is the hybrid OTEC system, or the plant, system that's been designed and developed by IOES, Saka University, and Genesis Incorporation as the technology provider, and already tested. And minimal testing has been done in Japan, and I think it was last year already tested in Japan. And we are in the midst, and we are eagerly waiting to receive this HOTEC system once our building for the UPM OTEC Center is completed, we'll be receiving. So we are already eagerly waiting to receive this OTEC system in order to do the test and technical evaluation using the surface seawater of the Teluk Kemang in Port Dickson. So next, we saw what are the definitions of renewable marine renewable energies, then which brought us to OTEC, yeah, in the marine renewable energy. Then we went on seeing what was the difference between the OTEC and the OTEC that we are doing in this project, current project. And moving on, what is the consequence or the relation, what's happening in Malaysia? So before we see what's happening in Malaysia, I would like to highlight the energy-related bodies in Malaysia. So under the Ministry of Energy and Natural Resources, this, of course, if you are a Malaysian, you'll know, has been changed several times. There are some uncertainty, even in our mind that we, used to be relating to MOSTI, but now the energy comes under the Ministry of Energy and Natural Resources. So this, and below them is the federal statutory bodies. One of it is the Energy Commission, the EC, and the Sustainable Energy Development Authority, SADA. Okay, I would like to highlight the E stands for energy and not electricity. Just a highlight. Why I'm highlighting, you'll see why is that later on. So then we have power generation companies, which were from the history, if you see, they were all GLCs, partially becoming, partially privatized. So we have this Tenaga Nasional Berhad, TNB, and then in the Sarawak, we have Sarawak Electricity Supply Corporation, and we have Sabah. In Sabah, we have Sabah Electricity, and the conglomerate Petronas, Petroleum National, is anchoring or championing the oil and gas in Malaysia and this part of the world, and also the world. And then many other GLCs, YTL Power, Genting Senyang, Senyen, Malakoff, EDA Global, and many more. Some are small ones and so on. Okay. So that being said, now I was focusing and highlighting SADA. There's a reason for that. So the renewable energies in Malaysia. So this is a recent report. Okay, the report is highlighted here, which was quite recent, early this year or maybe last year, end of last year. Malaysia Renewable Energy Roadmap, MyRER, by the Sustainable Energy Development Authority, SADA. So report by SADA with joint. If you get into this report here, you'll be able to see who were the stakeholders involved. So they are focusing on renewable energy, such as hydro, solar PV, biomass, and biogas. So our point, or what we would like to advocate here, is to include OTEC in the energy mix. And that's the reason why we are requesting or proposing this to happen. Why? Okay, they have put up a graph forecasting from 2020 till 2035. 2035 is the first time frame they've put forward. Of course, I think it should move on till 2050, because we have pledged for the Malaysia has pledged for the 2050 carbon net zero. So I think it should be shown. But as a first phase, is up to 2035. Sorry. So if you look at this highlighted, the numbers here, so the baseline in 2020, from the installer, this is actually the peak consumption. What is highlighted, 8,450 megawatts are the, from there, peak consumption, meaning to say those are the installed capacity, and the percentage from the installed capacity is highlighted as 23%. 23%. Moving on, 20 and business, they've highlighted business as usual and new capacity target. What is business as usual? Business as usual has been highlighted to be when we don't put in place or put forward changes, then happen. When we have the policy change and so on, then we'll able to achieve a higher level, which is a green line that's highlighted here. So the focus now is, of course, to put forward the policy change, go through the bill to go through, pass through the parliament and so on. And then we are focused and try to achieve the green line. That's the way forward. So in 2025, if you look at this, so it's the increase is going to be 31% from the 31% as renewable energy from the installed capacity. Then moving on, 2030 forecasting for it to be at 40%. So reach this of renewable energy, we cannot let. That's the reason why OTEC has to be included. Only with this hydro, solar, PV, biomass, and biogas, we are for sure unable to achieve this 40%. If you're really, in serious, then we have to include OTEC, and that's the proposal that we've put forward. Okay. Of course, I did talk about wind a little bit just now, because if you look at the report, wind is also mentioned, okay, in places. So wind potential. So this is just a highlight here. What is the wind potential in the world? Okay, and Malaysia to be more specific. Okay, so in the world, you can see I put two arrows here to really focus on the equator. Yeah, we are here sitting here in the equator, right, or near to the equator. So from here we can see that our wind is as low as the lowest here, about 4 or 5 meter per second, the speed of the wind. So this brings me to the next slide, which is to see typical wind turbine power output. And when you look at that, of course, the cutting speed is there, but for the generator to really generate the electricity or the production side of the energy, we have to have about 14, at least about 14 meters sec of wind speed. So what are we talking about? Having sitting in an area near the equator and having only 4 to 5 meter per sec, we are unable to achieve the 40% of renewable energy. Yeah, we can do. We can make do by bringing in the wind in the energy spectrum. Yeah, a renewable energy spectrum, but not as the main one having large capacity. So that is what we'd like to highlight here. Next, from the same report, the wind in Malaysia from the same report, MyRER. It shows that they've done quite a bit of study to highlight where do we have 5 meter per sec of wind speed. Somewhere in Lahad, is it Lahad Datu? I think here, yeah, the northern part of Sabah, and then of course the peninsula, the northern part of the peninsula, and trying to highlight how many kilometer, how many square kilometers the area which has the greater than 5 meter per sec speed. So that's where the technology that was highlighted for the wind turbine or the wind farm, wind generation in Malaysia has to be those turbine. It's not the off-the-shelf, what the temperate temperate cold countries in the northern and Europeans and so on. They are having. We can't bring that here and plug and play it here in this part of the world, in Malaysia. So we need to have a different type of wind turbine, which is called the low-speed wind turbine. Okay, so then which can accommodate and generate electricity with about 5 meters meters per sec of the wind speed that we have. That's the potential that we have in Malaysia. So now my question would like to highlight and ask. So what's the capacity of the wind turbine that you can think of for Malaysia? Is it going to be 1 megawatt or 10 megawatt scale? Okay, so that's just a question that I put forward. Okay, that brings us next to OTEC here. Yeah, worldwide potential ocean thermal energy driven development for energy. Yeah? Energy here, we'd like to focus on the hydrogen as a fuel, water and food supplies. So this was taken from the OTEC Foundation. You can refer to that. And OTEC potential is highlighted in red and orange here. And Malaysia is located and highlighted here in green. Now we go deep down into Malaysia. Potential. This has been, way back. Prof. Dato Bakar has been highlighting, anchoring, championing, and advocating that we have OTEC potential in Malaysia. So I don't really want to go into this part. However, you can check out this the paper that's highlighted here to get more details of our latest some of the activities. So many names are highlighted here as the potential site for OTEC, and this list is going longer. We have more names now of the sites, potential sites. So please do check it out. Then why this place? These sites are potential for OTEC because of the temperature and other profiles. Of course, Tawau, Simpadan, Kalumpang, Layang-Layang, Bangki, the temperature of the surface seawater being at about 27 degrees C, and the deep sea water at the depth of 600 meters to be at 7 degrees C. So this gives us a temperature difference, a gradient of 20 degrees C. Yeah? And then the salinity depth profile is profound, the DO depth profile is profound, and the water mass profile, the TS is profound for us to really confirm that these sites are beneficial and good sites for OTEC. Next, bringing me to, I hope I'm okay with the time. Okay, commercial OTEC plant. So if we can imagine, visualize, and design, and do some theoretical work to have a 10 megawatt of OTEC plant in Malaysia. But please take note, this is only for the closed cycle OTEC plant. We haven't really dived into the HOTEC because the project is still going on, and we are still validating. So for a closed cycle, yeah, this is to highlight if you want to have a 10 megawatt OTEC plant in the Sabah sites that I've mentioned earlier. Yeah, the 10 megawatt, the net power that we have put forward here upon deducting or omitting, minusing off the pump of the surface seawater and the deep sea water and the working fluid pumps, the 3 pumps, if you minus it off. So the net power that we can achieve is 8.6 megawatt. So from here, you're able to see what is the gross, from the gross of 10 power, we are able to achieve 8.6 megawatt. And you can see what is the percentage, right? It's about 86%. We are able to achieve the net power. And what would the flow rate be for us to achieve this? The flow rate approximately from this figure shown here, the cold seawater and the deep seawater is sitting, it's overlapping. So almost about the same, which comes and brings us to 4.5, 10 to the power of 7 kilogram per hour. This is just to give some idea of what is the flow rate that's required. So, of course, some assumptions are already made, whereby the cold seawater pipe length, 800 meters depth, and the seawater pipe diameters being at 5 meters. So this is to visualize and give an idea of what OTEC plant that we are thinking of, a floating type OTEC was already proposed by Genesis Incorporation, conceptual idea. So we did some further calculations and theories, and we come up with the latest programming methods that we have used. So if we can have an OTEC plant in the size of 10 megawatt, 100 megawatt OTEC plant, we can happily use it for the production of green hydrogen and green ammonia. Okay, so this is just to give you an idea, and this idea was put forward by Lockheed Martin way back then. But yet to materialize in the world. So this is an idea of offshore OTEC plant, whereby the tanker will be coming to pick up the green hydrogen and the green ammonia for mainly to tackle the carbon net zero issues and so on. So that's the idea that we put forward, and why we have a reason actually why we have to do that, or we are proposing that, is that this is an article, corporate news from the Petronas ENEOS MOU to explore green hydrogen production. So it is already happening, yeah. And article September 2021, yeah. So the overview of potential collaboration between this Petronas and ENEOS, what they've proposed and put forward. The supply chain or the line is already well developed. So of course, for the renewable energy, they have put here a wind turbine. This is most probably is offshore wind, and also solar PV. So it's okay. We are not saying not to utilize offshore wind and solar PV. In order to upscale, please also consider on-land or offshore OTEC plant, which will directly supply the energy for the electrolytic cell and the production of green hydrogen. So, of course, in Malaysia, Petronas petrochemical plants are already manufacturing and producing in a small scale, but however, for moving forward, for the green fuel that we are talking about, especially for the carbon net zero, this upscaling is very much vital and important. So that's where, having the OTEC here, because the supply chain is already developed, yeah, and then transporting, of course, transport of the MCH to Japan, and then of course once it arrives, then the tooling back to the production plant, and this hydrogen will be utilized in the power plant, steel plant, and fuel cell vehicle in respective countries. In this example is Japan. All right. So that being said, so what is going to happen? Hydrogen production in ASEAN by 2040. Okay. I would like to apologize that to date, I don't have what is it currently, but this is something that we have to do by 2040 or for 2040. Yeah. So the y-axis, the unit is in million ton of oil equivalent, and highlighting many countries. Of course, countries in ASEAN, Brunei, Cambodia, Indonesia, Laos, Malaysia, Myanmar, Philippines, Singapore, Thailand, Vietnam. And here, we would like to focus and look at what is Malaysia. So Malaysia is already supposed to produce by 2040, using fossil fuel is there, and then the renewable energy part, producing about 20 million ton of oil equivalent. So hydrogen production potential in Malaysia, approximately coming to here, using the renewable energy, 20, which I mentioned earlier. So what is the renewable energy that they've highlighted or focused on? Is solar power, hydropower, and biomass. Okay. So what we would like to put forward is energy mix is important. Thus, OTEC technology is also vital. So please incorporate OTEC and produce hydrogen, the green hydrogen. So that being said, you can get the links from here highlighted. Brings me to the end of my talk. I hope my time is okay. The way forward, the way forward and OTEC in Malaysia. Definitely, a viable business model to sustain the OTEC commercial plant is important. But we have huge conglomerates such as Petronas and so on. See, so this wouldn't be an issue. Yeah. So such viable ideas and the business model must be worked together. Yeah, in order to achieve OTEC commercial plant. And then OTEC Technology for Education and Talent Development, as we are coming from the University of Technology Malaysia. So education is something that you can't leave behind. It has to continue for years and ages so that the next generation will be groomed and developed. And then firm policies must be put forward to sustain the OTEC technology. So with that, we hope that OTEC to engineer a better world for you and I to stay long. So with that, I thank you for listening. Thank you everyone for listening. And if at all any question and answer, I will pass it back to our moderator, Dato' Baka.
Yes, thank you very much, Dr. Satya. Excellent presentation. Because we lost some time earlier, so there are three questions posed in the chat. So what I'll do is I would encourage you to respond to those three questions, Dr. Satya, to the chat box. Then we'll revisit those questions. Then we'll should go on first, and hopefully by the end of the session we have time to revisit those question and answers at the end of our session. So I think we need to catch up a bit of time. We lost some time already.
Okay, Dato'. Thank you.
Yeah, I hope you can do that. Okay. I hope the two questionnaires, those who raised the question will be, please bear with us for a while. Okay, now I have the honor and pleasure to introduce our second speaker rather, Dr. Yoon Yang Chun. She received her PhD in 2014 from Aijo University in South Korea and worked at Korean Railroad Research Institute. And since 2020, she has been working as a researcher at the National Institute of Advanced Industrial Science and Technology, in short, ICE, under the Advanced LCA Group, Life Cycle Assessment Group. And her main research area is life cycle assessment and eco-design for sustainability, and she is heavily involved in one of our 10 projects, in particular project output number 4 from the Japanese side. Now I have the honor and pleasure to invite Dr. Yoon Yang Chun, and she's going to touch on the subject of life cycle assessment and its application on our hybrid ocean thermal energy conversion plant. Dr. Chun, you have the floor now. Thank you. Dr. Chun, you have any problem? Yeah.
Good morning, ladies and gentlemen. My name is Yoon
Yes,
Chun
we hear you.
from
Yeah, very good.
Today, as a representative of ICE members and one of the participants for the HOTEC Output 4 project, I would like to talk about life cycle assessment as a tool to quantify the environmental impact and its application on the HOTEC system. For today's talk, I will briefly explain life cycle assessment, so-called LCA, and how and what we are doing with this method for this project. What is LCA? When we discuss about the environmental laws, environmental impacts, environmental performance, or sometimes greenhouse gas emissions of a certain product, we do not hesitate to mention LCA because LCA is a systematic tool and also a globally standardized method to quantify all the environmental aspects of a product or a service system along its entire life cycle. Considering the impact of a product along its life cycle indicates, we include and we consider all the emissions from the downstream and upstream of a product when quantifying its environmental impacts. The life cycle includes, as you can see in this slide, raw material acquisition by mining activities, parts and component production, final product assembly, all the transportation between each activities, energy consumption during product use, and finally end-of-life treatment activities such as recycling, reuse, incineration, and ultimate disposal. Thus, LCA assesses accumulative potential environmental impacts of a certain product, and it also enables us to document and improve the overall environmental profile of the product. LCA can be used to quantify the environmental impact associated with industrial products technologies, and services through their life cycle from cradle to grave, indicating from raw material acquisition to end-of-life stage. ISO defines the pages of LCA as goal and scope definition, inventory analysis, impact assessment, and interpretation. Among those pages, inventory analysis is the most page required for time and labor. Life cycle inventory analysis involves creating an inventory of flows from and to nature for a target product system. It is the process of quantifying raw material and energy requirements, emissions to air, water, and land, resource uses, and other releases over the life cycle of a product or service. In other words, it is the aggregation of all elementary flows related to each unit processes within a product system. Lifecycle inventory analysis is followed by lifecycle impact assessment page. Lifecycle impact assessment aims at evaluating the significance of potential environmental and human health impact resulting from the elementary flows determined in the lifecycle inventory. Lifecycle inventory analysis and impact assessment, accordingly LCA results, depend on the goal and scope of LCA study. For this project, our goal is to evaluate the potential greenhouse gas emission of our OTEC and Malaysian model. So based on this goal, our LCA study is performed. By using LCA, we can also identify key issues, that is weak points of my product, to improve for redesign. As I explained previously, one key challenge in LCA study is that we need to put a lot of time and labor to compile inputs and outputs of our target product. It would be impossible to generate data on the all unit processes in a product system. This is why it is important to distinguish between foreground and background data in LCA study. Background data typically comes from lifecycle inventory database, so-called LCI database. One of LCI database is IDEA, which is made by ICE that we mainly use for this project. The foreground data are the data of foreground processes which are under control of the decision maker for which LCA study is carried out. For our project, data especially related to design and development of OTEC and the Malaysian model are treated as foreground data. Once we define and gather background and foreground data to compile inputs and outputs of our system, we can finally quantify the environmental impact resulting from the all elementary flow related to all data and unit process information collected. As mentioned earlier, this refers to impact assessment page. Depending on the purpose and goal of LCA study, we select impact categories. Common impact categories are global warming, acidification, ozone depletion, human toxicity, and etc. The LCI results are assigned to the chosen impact categories based on their known environmental effects, further transformed into the results within each impact via equivalence factors to create impact category indicators. For our project, we chose global warming as impact categories, and as a result, we can get results contributing to global warming impact expressed as CO2 emissions. This slide shows the example of CO2 emission results of 1 megawatt OTEC that has been simulated for Kumejima model in Okinawa. In Kumejima model, LCA results indicate that the construction stage, especially intake pipe, and heat exchangers are key issues to be improved in terms of greenhouse gas emission. This is another example of LCA study for OTEC systems. This figure represents CO2 emissions per 1 kilowatt-hour electricity generation by different type of OTEC system, solar and wind power plants. The red graph shows the result of the Kumijima model in Okinawa. All these results are based on simulated model, while Kumijima model here from this graph represent 1 megawatt OTEC. The real model is operated under 100 kilowatt condition. Anyway, after performing LCA for our HOTEC model and the Malaysia model, we believe we can also compare our CO2 emission results among other models. We define our system boundary of HOTEC as shown in this slide. We collect foreground data related to construction consisting of material acquisition and production, installation and use, and disposal. As background data for upstream processes of HOTEC system, we use IDEA database. IDEA comprises more than 3,800 background data sets, so we can easily search and use those data sets required for HOTEC LCA study. This is the list of foreground data of HOTEC main equipment, seawater piping, and building that we have obtained from the field. Sometimes it may have difficulty in accessing foreground data at enough level to use for the study. For instance, we obtain foreground data regarding piping, but it contains only size information. If detailed material and weight information is not available, of course we'll try to gather detailed data, but sometimes we may have to use the modeling results based on assumption. This slide shows the tentative results of HOTEC system based on the data gathered so far. Since we've collected foreground data primarily from material acquisition of HOTEC, the contribution analysis results are focused on embedded greenhouse gas emission from material or parts. Once we complete collecting foreground data from all other life cycle stages, the contribution results will be changed. After collecting all foreground data and connecting background data required for HOTEC system, the future image of contribution results would be like this, though the real value and length might be different. This graph indicates the contribution of life cycle stage of OTEC to the total CO2 emissions. As you can see, according to Arbor's study on 10 megawatt OTEC installation, raw material acquisition stage is the highest contributor, followed by transport and then manufacturing. While we do our LCA study to evaluate the potential greenhouse gas emission from HOTEC system installation and to identify key life cycle stage or key issues of HOTEC, we can also use LCA for another application to evaluate the effect of some changes or design options such as material selection on greenhouse gas emissions, thus highlighting the improved environmental performance of these changes. For instance, we could compare greenhouse gas emission from the evaporator and desalination condenser between OTEC and HOTEC, since some material in HOTEC has been changed from titanium to stainless steel. Originally, seawater passed through the heat exchanger in the OTEC system. So OTEC used to have 440 kilograms of titanium for corrosion resistance function. However, in HOTEC, water vapor passes through the heat exchanger, so we don't need to care much about corrosion resistance issue. So stainless steel is used instead. We know this is not because of environmental issue, but as a result, we found that this material change for evaporator and desalination condenser could actually reduce photon CO2 equivalents in the equipment in HOTEC. This is just one example, so we can use LCA to identify or compare any effect of any other example, such as material selection or design alternatives for HOTEC on greenhouse gas emissions. The options for sustainable electricity generation are various, such as wind, solar, hydropower, biomass, and geothermal plants. Of them, ocean thermal energy conversion, OTEC, is a technology that can be implemented as a promising sustainable renewable energy solution at this moment. However, the HOTEC system has a considerable size, such as long length of the water pipe. It also requires the large area requirement for heat exchange, leading to non-negligible environmental impact. So, it is necessary to investigate the environmental impact of the full life cycle for HOTEC system. In order to do this, we use LCA. LCA is a systematic tool to quantify the environmental impact. In other words, the environmental performance of HOTEC and further Malaysian model. Based on foreground and background determined so far, greenhouse gas results are quantified, but primarily focus on construction stage, especially from raw material acquisition so far. So with aid of manufacturer and other project members, we hope to successfully list up all foreground data and also define installation, use, and disposal scenario soon to complete the big picture of HOTEC's life cycle impacts. Our expected results will allow us to eventually evaluate the potential life cycle environmental impact of HOTEC in terms of greenhouse gas emission, and it also enables us to compare the environmental performance of various design options or suggestion for better design in terms of environmental impacts. This is the end of my presentation. I was very glad and happy to present this in front of you guys. Thanks for your kind attention and listening. Please feel free to ask me if you have any question. Thank you.
Thank you very much, Dr. Chun. Excellent presentation, very clear. And I think there's one question, not necessarily targeted to you, but we can try to respond. This is a question by my colleague, Engineer Lal Chan. If not, anybody else could come in, and Dr. Satya and others could help to answer that question. Now we almost caught up with our schedule. Thank you again, Dr. Chun. Excellent, very interesting presentation. And now I have the honor and pleasure to introduce our next speaker. Is our colleague, Associate Professor Technologies, Dr. Muhammad Khairi Abu Hussein. He is now Associate Professor at Razak Faculty of Technology Informatics, UTM. He received his first bachelor degree as well as his PhD at the University of Liverpool, UK. He's published a lot, and he also is a professional engineer with the Board of Engineers Malaysia. He's a professional technologist with Malaysia Board of Technologies. He's a chartered engineer and chartered marine engineer with the Institute of Marine Engineering, Science and Technology of UK. Today, Dr. Khairi serves as a Deputy Director of UTM Innovation and Commercialization Center. Prior to this, he was a Deputy Director of UTM Ocean Technology, Ocean Thermal Energy Center. And he also a co-founder of the SATREPS Smart Solution, is a registered spin-off company of UTM. And that company provides technical consulting services to evaluate offshore platform reliability and performance. And he specializes in offshore structure modeling, hydrodynamic, wave loading simulation, wave mechanics, reliability and risk assessment of offshore structure and structural health monitoring. Now I have the honor and pleasure to invite Professor, Associate Professor Engineer Dr. Muhammad Khairi. You have the floor now, Khairi.
Thank you very much, Prof. Dato' Abu Bakar. I have basically prepared the pre-recording video, so I hope community can play the video. Thank you. Wabarakatuh and good morning. My name is Muhammad Khairi Abu Hussein from University Technology Malaysia. It is my pleasure to be part of the second SATREPS OTEC forums. And for this slot of presentation, I would like to share our latest research finding for the development of offshore peak platform application for ocean thermal energy conversion power plant. For this research, we collaborate with the University of Liverpool, United Kingdom, and our industrial partner is Repsol Malaysia, Sdn Bhd. Very brief about the project background. OTEC utilized a special working fluid which have a low boiling point. And then with this, once the working fluid, for example, ammonia pass the evaporator, they change the form from liquid to vapor or gas. With this high pressure gas, the turbine can be run and the energy can be produced. And then the rest, basically, the working fluid will change back from the gas to liquid and continues. And then based on this, you can see that we need to pump surface water and also deep sea water in order to make sure the system work properly. From this water, basically, you not only can produce energy from OTEC technology, but at the same time, we can use the water that we pump from the sea for many purposes. For example, from the desalination activity, we can produce pure water, and from pure water, we can utilize this pure water to be a potable water, or at the same time, we can use this pure water for purpose of the hydrogen production. And at the same time, from the desalination activity, we can basically produce mineral water, and also at the same time can use this water for the activity related to aquaculture or agriculture. Here is about the current development of OTEC worldwide. There are several power plants have been installed either in Saga, Japan, or in Goshen, Korea, and also in Okinawa. So far, the highest or the biggest power plant available worldwide is about 105 kilowatt, which is in Hawaii. And at the same time, there are a lot of effort or activities worldwide try to utilize this technology to produce energy and also to use this water for their to support their life. Okay, based on the data that we basically gather, we can see that the development of OTEC at the moment utilize either the land-based facilities or offshore floating power plant. Okay, but it depends on the location and also the need of the projects. For example, if the location is quite far from the land, obviously they basically at the moment can utilize the offshore floating power plant. But the thing is, to deploy the offshore power plant, it involves very high upfront capital cost. Here is the challenge for the OTEC commercialization activity. I can basically categorize them for three different perspectives. For example, number one is about the financial perspective. As I mentioned earlier, the large-scale OTEC plant normally require high upfront capital cost. For example, for 50 megawatt offshore floating structure, it normally involves about 500 million USD for the capital investment. Okay, and that's number one. Number two, in terms of the environmental perspective, since there is no commercial scale power plant has been installed anywhere worldwide, there are a lot of concern about the impact of this installation on the marine life due to the water that we pump and then also due to the water that we discharge back to the sea. Okay, and then in terms of number three, we can see as well in terms of challenge or in terms of the technical perspective. So far, there are a lot of concern about the lack of experience of building the commercial OTEC power plant, which high magnitude or high scale. And one of the concern basically is about the impact of the biofouling on the pipes, and then also the corrosive environment impact to the structure. In this study, basically, we focus more toward the financial perspective, and we try to venture a possibility to utilize the peak offshore platform in order to minimize the capital cost of the development. Based on the recent study, for peak for the floating offshore structure for the purpose of OTEC installation, we can confirm that most of the capital investment basically contribute by the platform and moorings, and then also the heat exchanger of OTEC facilities, and the balance is basically allocated for the deployment and installation of the technology. So from this information, we can confirm that if we can give another opportunity or another option for the platform and moorings, the percentage that contribute for this capital cost can be reduced. Therefore, in this study, we try to venture the possibility to utilize peak offshore platform to reduce this capital cost. Why peak offshore platform? Because the peak offshore platform is very common and very common in oil and gas industry, and the technology is already matured. Therefore, there are 4 research objectives we have been set for this project. Number one, to refine the OTEC system configuration for peak OTEC platform. Number two is to fabricate the prototype of the peak offshore platform. Number three, to evaluate the prototypes. And the last one is to do the assessment on the techno-economic viability of this proposal. Okay. In terms of the methodology of these projects, we basically divide them to 5 stages. The first stage is more toward the environmental data collection and also the mid-ocean data. So from this data, we basically can identify the suitable peak offshore platform that we can utilize for the purpose of this study. And then after we identify this information, we confirm what kind of platform we want to utilize. We can start with the structural modeling and analysis. For the structural modeling and analysis, normally it involves a lot of activity related to front-end engineering design, from modeling, the pushover analysis, and also the structural reliability analysis. Based on the detailed design we produce from this stage, we will basically produce or fabricate the prototype of this peak offshore platform and do the testing in the laboratories, which cover in stage 4. And then the last one, based after we confirm that the suitability of the performance of the power plant, peak offshore OTEC power plant, we will conduct the techno-economic assessment in order to see how the capital cost, how the impact of this technology can reduce the capital cost of the investment. Okay, the research objective basically mapped here. We can see that RO1 covered until the structural analysis, RO2 covered up to the fabrication prototypes, and then RO3 and RO4 for the purpose of laboratory testing and also techno-economic assessment. So far in Malaysia, we found that there are several locations is suitable for the installation of peak offshore platform. For example, in Kuala Barang, Pulau Layang, Pulau Penyu, and Pulau Balambangan, and also Sampurna province. Based on the recent study that we conducted in Malaysia, we can confirm that there are about 130,000 kilometer square area that suitable for OTEC developments. And from this area is about 105 megawatt electricity can be produced. In this study, we found that Pulau Sipadan and Sampurna province is one of the most suitable location can be utilized for the OTEC offshore or peak OTEC offshore power plant. There are several reasons for this. Number one, because of the location to the nearest island is quite viable, and number two, in terms of the piping length is quite suitable for the purpose of the peak offshore OTEC installation. From this information, we can see that between the 100-year water depth to the land is less than 1 kilometer, and in terms of the distance or the length of the deep sea pipeline, up to 800 meter water depth is only less than 3 kilometer, which give very huge advantage in terms of the capital cost of the investment. And at the same time, from the 100 meter water depth to the land or island is less than 1 kilometer, which can also reduce the cable, subsea cable installation for this technology implementation. Here is part of the preliminary output from this project, which has been conducted from our previous research grant. Based on this information, we managed to establish 1 megawatt closed cycle OTEC system. From this information, we can confirm that several equipment that need to be installed on the platform, and also the dimension for each component. And based on this information, we do the proper estimation in terms of weight, because for the peak offshore platform, there are two important criteria or component that we want to measure. Number one is about the space or the dimension of the facilities or equipment. Number two is about the weight of the equipment. So based on this study, we found that the total weight for 1 megawatt closed cycle OTEC is about 300 metric tons. Okay, based on this 300 metric ton, the monopod or single leg platform is suitable to cater the need of the installation of this OTEC system. So here is the schematic of 1 megawatt OTEC offshore power plant. So we can see all the components that introduced in earlier slide has been properly positioned in the on the platform. And in offshore peak OTEC power plant, there are two main piping has been installed. Number one is the deep sea pipings, and number two is the discharge piping. So the impact of this piping is very huge for the platform performance because of the drag coefficient. Drag force will be high due to this piping. And in this study, we do some analysis to confirm the impact of this piping to the overall platform performance. Based on the design that we conduct and based on the analysis we conduct, we can confirm that the reserve strength ratio, the probability of failure, and also the return period of this platform still can be utilized. under the ISO and also API code. And based on that information, we finalize or we produce the detailed design of the structure for the purpose of the prototype fabrication. So we can see from here one monopod power plant with the 1 megawatt OTEC equipment installation with the proper engineering design have been produced based on this study. And based on this detailed design, we will basically produce 1/40 prototype, steel structure prototype for the laboratory testings. We don't complete the laboratory testing yet, but we basically will do this laboratory testing somewhere early next year while waiting the funding from our grant application. So for your information, here is the detailed illustration of the 1 megawatt peak OTEC platform, which located somewhere in Sipadan Island. We can see that while with having this technology in Sipadan Island, it not only can produce energy and supply the energy to the nearest island, but at the same time, based on the water that we pump here, we basically can channel this water back to the island and utilized by the people who live in Sipadan. Very brief about the development of course based on the peak offshore OTEC platform. We conduct two possibilities. Number one, we use the single leg platform for monopod, and also we also conduct the four-legged OTEC peak offshore platform plant. So based on this information, basically we considered several information input which basically provided by our industrial partner. So there are 7 parameters or 7 activities involved, from project management to the conceptual of the platform designs. And then we also considered about the bathymetry survey and soil borings survey. And then OTEC equipment and also prototype design also in our calculation. And the last 3 is more toward the procurement of the technologies, the engineering and construction, installation and commissions, including the production of the structure plant, structure platform and equipment pipeline for water intake up to 5 km at Sipadan Island, and also the installation of subsea cable up to 3 km from the peak OTEC platform to the islands. Okay, from here, we conclude that the overall cost of the investment for 1 megawatt peak offshore OTEC power plant is about 37 million USD for monopod structure. And in the case of four-legged structure, which have a bigger platform, and in future we can basically increase the magnitude or the capacity of the OTEC. In here, we can see that the total investment capital cost is about 132 million USD. Based on the monopod, what we call costing, the current study found that for the 1 megawatt capital cost normally somewhere between 45 to 75 million USD. And based on the information, the preliminary findings, we can confirm that the application or the installation of peak offshore platform for the purpose of OTEC installation significantly reduce the capital cost of the investment of this technology. In terms of the expected result from the application of this technology, number one, as I mentioned earlier, is to lower down the capital cost of investment. As I mentioned from the previous slide, our preliminary finding confirmed that the 1 megawatt OTEC power plant, this objective can be fulfilled. Number one. Number two, the same offshore OTEC power plant as well can reduce the impact of this technology to the environment. Because for your information, there are more than 50% of peak offshore platform at the moment more beyond their cycle. So they need to decom this platform, and decommissioning normally have the environmental impact. So by utilizing the aging offshore platform as a plans for this OTEC technology, the impact of the environment of this activity can be reduced. And then at the same time, OTEC can be properly mapped on several SDG, for example, SDG 7, 13, and 14, which clearly contribute to the UN SDG goal. And at the same time, for the Malaysia cases, OTEC power plant as well can also contribute to the Malaysian energy policy, which want to achieve at least 20% of clean energy generation by 2030. Okay, and also it very well met with the KEGA activities for the key economic growth area in Malaysia. And as a conclusion, based on this study, we believe that the application of a peak OTEC offshore platform not only can reduce the capital cost of the investment, which will be very attractive for the purpose of commercialization. But at the same time, with this kind of technology, the commercialization activity can be speed up, and the output from this study can directly implemented to one of the project, to the proposed project in coast of Sabah. Thank you very much for your time and your listening. And now I open for any question if anyone want to have any clarification for me. Thank you very much.
Thank you very much, Prof. Khairi. Thank you for having promoted, I would say, the third version of the OTEC platform. One is land-based and the other one floating offshore, but now you're promoting the fixed platform. I think this is another alternative to the structure. I think the application is very wide also in this design. And those who have questions to Prof. Khairi, please put in the chat box. We'll come back to you, and Prof. Khairi could respond your question in, through the chat box, as what has been done by Dr. Satya earlier to the question that we posed earlier. So now we are past 3 minutes in the scheduled time, but now I have the honor and pleasure to introduce our next speaker. And our next speaker is none other than our colleague, Professor Dr. Takeshi Yasunaga. He received his PhD in 2008 at Saga University, and he used to work at Mitsubishi Heavy Industries for 7 years, and he has been with Institute of Ocean Energy, Saga University, since 2015, and he is our close counterpart and working closely with Professor Yuki Ikigami. And his main research interests, other than the Ocean Thermal Energy Commission, but also working on desalination, organic Rankine cycles. And for the SATREPS OTEC program with us in Malaysia, is the project manager, is a counterpart of Dr. Satya from the Japanese side. Dr. Yasunaga, you have the floor now.
Thank you very much, Dr. Prof. Dr. Bakao. Can you hear me, and can you see my slides?
Very clear. Yes, very clear.
Okay, so good morning, everyone. I will be presenting a progress focusing on plate-type heat exchanger development for hybrid OTEC system. Okay, firstly, I'd like to introduce the characteristics, potential, and development status of OTEC very shortly. It will be repetitive information. So using the ocean thermal, which is the surface seawater around 25 to 30 degrees Celsius, and deep sea water 5 degrees Celsius to 10 degrees Celsius, around 600 meter to 1,000 meter depths. So firstly, we can apply the the so-called OTEC, ocean thermal energy conversion, to achieve the electricity, and which is the stable renewable energy. And also from the effluents, we can provide the water in this using this thermal energy, and also we can supply this deep sea water to the other industries. So ocean thermal energy can supply sustainable power, water, and foods. So potential of OTEC in the world is mapped here. As you can see, around the equator, you can see more red zones. And so we can see that around the equator of the ocean, they have much potential, including Malaysia. So this picture shows the projects of OTEC in the world. So we can see several projects in the pipelines here, and we can see some project pilot plants in Kumejima and Hawaii, also the demonstration plant in the South Korea. Let me introduce shortly these plants. The firstly, the left side is the Kumejima plant. In Okinawa, it's 100 kilowatt, and the right side is the Hawaii's plant, the 105 kilowatt in the Ocean Energy Research Center in Kona. So those plants are the closed ranking cycle, and the more bigger plant is demonstrated in the South Korea in 2019. 1 megawatt plant barge mounted for testing purpose. So in South Korea, Research Institute of Ship and Ocean Engineering, which produced the 338 kilowatt by temperature difference, 24.8 degrees and 6.1 degrees Celsius near the Busan coast. And this equipment will be installed in Kiribati Island, Kiribati country, and now it's waiting for to calm down the pandemic. So let's move to the hybrid OTEC system development under the SATREPS project. So let me introduce the concept of a hybrid OTEC system. Before I go to the hybrid OTEC system, let me introduce the conventional OTEC and seawater multiple use here. So left side, we can see the power plant here, which is very simple, and we can see we can use the surface seawater as a heat source and the deep sea water as a heat sink, and operate the heat engine using the working fluid. That is a power plant side. On the right side, we can also produce from the effluent from this plant. This plant means that from the OTEC. So this seawater still have the temperature difference. So using this temperature difference, we can produce the water by vacuuming the surface seawater and condense by using the deep sea water. So here, so the conventional OTEC and desalination are able to connect. However, they are independent. But in this hybrid OTEC system, I use the combination of the water and the power production. So firstly, we vaporize the surface seawater by vacuuming here and make steams. And the steam go to the heat exchanger and produce the water by cooling the working fluid of the heat engine. And the deep sea water will cool this heat engine. And also these effluents can be used for the other industries. That is the concept of our hybrid OTEC system. So what is the benefit of the hybrid OTEC system? And that is that they have three functions mainly. The first one is the prevention of the biofouling in the heat exchanger. So if we use the seawater directly to the heat exchanger, the biofouling will be occurred in the narrow space of the heat exchanger. But if we use the steam instead of the surface seawater itself, so the steam can condense in the heat exchanger, but no biofouling will be happening. So the second one is we can apply the low-grade materials because we cannot use the seawater directly to the heat exchanger. So we can use not titanium if we use the seawater to as the heat source, And the plate type heat exchanger, we should use the titanium for the material, but in this hybrid case, we can use the steam, so we can apply the more low-grade materials for the heat exchangers. The third one is the increase of the heat transfer performance. It means if we use the surface seawater as a heat source, there are no phase change and will flow in the inside of the heat exchanger. But if we use the steam, the heat transfer performance will be increased because the heat transfer mechanism will be changed to the condensation. The condensation heat transfer is generally more higher performance rather than the forced convection. So these are the function of the HOTEC system. So if we design the hybrid OTEC system in the for the commercial, we firstly consider the design condition at the location, and secondly, we should do the basic design for such as heat and mass balance. So in this heat and mass balance, we should consider the components of the performance to consider the how much heat will be transferred to the heat engine, or how much pressure will be occur in these systems, to consider the backwork in the system. So if you look at the flow diagram of the HOTEC system, the right side is the power generation side, and most of them same as our facility or the facilities in Kumejima, demonstration facility in the Kumejima. So on the left side, if we look at the flash chamber, the desalination part, this desalination has already produced in and operating in India and our facility as well. So the key will be this evaporation condenser we call the evacon. We need this experimental data to design for the system. So the target of this research is to achieve the non-dimensional empirical formulas on heat transfer coefficient for the design of the evaporator condenser in large-scale hybrid OTEC system. So what is the evaporation condenser? So we call the evaporation condenser because the left side, the one side in the plate, between the plate, will be the condensation of the steam. And the other side will be the evaporation of the ammonia. So we call the evacon in this plate type heat exchanger, and we mounted the small scale heat exchanger in this equipment and tested in our facility. So let me explain about the system of this small scale evacon system. The seawater will flow from the bottom side and go into the flash chamber in this first flow, and some pressure of seawater will evaporate, and the steam go through the demister and condense at the evacon, and we will produce the water. And the ammonia will flow to the evacons from the bottom, and the vapor will go from the outside, so upflow. That is upflow. So now right side table shows the specification of this evacon heat exchanger, and the size is 300 millimeter, and the width is 700 millimeter, and very small one, and the number of plates is 30 plates, and total heat transfer area is 6.7 meters square. So the experimental condition is here. So we tested 3 different temperature and also the mass flow rate of the seawater. And the ammonia mass flow rate is adjusted to not to dry out at the outlets of the evacon, so not fully evaporate the water ammonia. And to analyze the experimental data, we firstly measure the overall heat transfer coefficient by using the heat transfer rate and also temperature difference between the ammonia and the water vapor side. So we can calculate the overall heat transfer coefficient U here, and we need to estimate the heat transfer coefficient for each side. So in general, if we consider the evaporator or condenser, the one side is no phase change and the other side will evaporate or condense. So in that case, we can apply the Wilson probe method, which is assume that in the overall heat transfer coefficient, one side of heat transfer coefficient is much smaller than the other side. So this technique is can be assumed as a function of the one side of the velocity, or I said here the Reynolds number, but it's please consider it's that the Reynolds number is just a velocity. So but in case of EVAPCOM, of the both sides of the heat transfer accompanied with the phase change. So we applied more statistical method that is firstly we assume the empirical formulas here by considering the current research, the other researches on the plate-type heat exchangers, and then we make it optimized problem by minimizing the experimental overall heat transfer coefficient and analyzed overall heat transfer coefficient. Okay, so I'll show some results of the overall heat transfer coefficient first. If the left side is a mass flux, the overall heat transfer coefficient as a function of the mass flux of the water, the steams. And the right side is the overall heat transfer coefficient as function of mass flux of ammonia. So if we look at both the diagrams, we can say by increasing the mass flux of both sides, the overall heat transfer coefficient tend to increase. However, it's very difficult to realize the more details relationship between the both mass flux or the properties of the both sides. So again, we applied the more statistical method to determine these constants. Then we achieved each constant by minimizing these errors, and finally we achieved the plus minus 25% of the overall heat transfer coefficient. Okay, so the final result, we finally achieved the empirical formulas for this plate-type heat exchanger of EVAPCOM. And also we assume that the one side is a perfect fit for the heat transfer coefficient and analyze the other side of the heat transfer coefficient. So if we look at the condensation side in the left side, the empirical formula can be fit in within plus minus 20%. And if we look at the boiling, the empirical formula has wide error compared to the condensation. So what we can learn from here is that the condensation heat transfer is dominant thermal resistance. That means the condensation heat transfer is much smaller than the boiling heat transfer coefficient in this experimental conditions. Okay, so let me summarize this presentation. In the SATREPS project, hybrid type OTEC is developing, which is power generation and produce the water simultaneously. And the key component of the hybrid OTEC is plate type heat plate-type evaporator condenser, the small-scale evacon heat transfer performance was conducted and reviewed the heat transfer performance, and we finally achieved the empirical formulas for each side. And lastly, considering the data variability of empirical formulas, the condensation heat transfer may be dominant thermal resistance in the evaporator condenser. Okay, thank you very much for your attention, and thank you very much.
Thank you very much, Professor Takeshi Yasunaga, for your excellent presentation, and you described very detailed on our OTEC component, a major component on that evaporator as well as heat exchanger. Very interesting, and I hope if any participant would like to pose any question to Dr. Yasunaga, you're welcome. Please put through the chat, and I'm sure Dr. Yasunaga will be able to respond to your question through the chat. I will revisit any response that you think you need further clarification afterwards. Now I have the honor and pleasure to introduce our next speaker. Is none other than our colleague, Dr. Firdaus Muhammad Yusuf. She's a senior lecturer in the Department of Environment, Faculty of Forestry and Environment, previously known as Faculty of Environmental Studies, University Putra, Malaysia, and she has been with the university since 2011. And recently, she was an associate researcher at the International Institute of Aquaculture and Aquatic Sciences, University Putra, Malaysia, in July 2019. And Dr. Firdaus also headed the Environmental Forensic Research Center, in short, ENFORCE, during the period September 2014-2016. And she has 10 years of experience in marine pollution research, malacology, ecotoxicology of organic pollutants, metals, and isotope markers. She has published over 100 journal and publications in journal proceeding and books. And Dr. Firdaus also led 3 research projects related to shellfish farming in Malaysia. Ofish 2 projects have been completed and 1 is still ongoing, as well as leading a knowledge transfer project related to the conservation of shellfish habitat. Recently, Dr. Firdaus had received the gold medal in the Sulam category in the Putra Creative Carnival in Teaching and Learning, TL 2020, and the team she led won 3rd place in the Pertaniangan Amalan Terbaik Inovasi and PNP antara faculty, schools, among faculty, schools, and energy centers of UPM 2021. And she also received the Best Community Project Network Academic Staff category in 2016. Okay, Prof. Dr. Firdaus, now you have the floor. Thank you.
Assalamualaikum and very good morning, everyone. I'm Dr. Firdaus binti Muhammad Yusuf from University Putra, Malaysia. And today I would like briefly introduce source identification of heavy metal contamination in aquatic environment using lead isotopic signature. Okay, with the rapid development, urbanization and industrialization, large amount of trace metal from anthropogenic sources are discharged into our environment through various pathways. And once a non-point source contamination occurred, it is often difficult to identify the sources. Yeah, and what we can see, we only notice the existence of the contamination due to the changes of the water body or presence of mass mortality of the aquatic life, such as example here, the mass mortality of fish at Sungai Damansara and whitish color of foreign material on the surface of water at Sungai Masai, Johor. And this non-point contamination source is not only limited to sungai or river in, yeah, usually it's also can occur at coastal environment where tourism spots, usually related with tourism spots. And this is, if we see the rapid development at Port Dickson before the pandemic took place, okay, the data shown here between 2016 and 2018, number of visitors, percent of hotel occupancy, and population size at Port Dickson that drastically increased between these 5 years of the data, and this data is from Department of Statistics Malaysia. Okay, and once the contamination occur at water body, is not only harming indirectly but mostly directly to residents that live on nearby area at the contaminated site. Okay, that's the reason why we always in Selangor we always experience water shortage or unscheduled water shortage due to this kind of pollution incidents that's really uncontrolled previously. Okay, and it affects indirectly to inland fishermen as well, like shown in the slide here. And when we're talking about non-point source, usually, okay, hard to identify. The reason is the pollution sometimes is not originating from close by area to the water body. If you look at the slides here, it's indicating that the contamination is actually occur far from the water bodies, far from the river. It is buried tank. Okay, there is a leaking at the around the buried tank for this factory. Okay, due to the condition of the soil structure and the characteristic of the chemical, it can seep into the underground water, and then with this flowing water table, it will just transferring or translocating the contaminant to much further or far away from the point source. Okay, and if this scenario happens, it is hard to identify from where is originating. And what I understand, like Selangor state government bought several drones just to investigate this kind of incident to control what river pollution. Yeah, but previously, okay, what's popular? The popular approach to identify the source of contamination is using statistical analysis, and this statistical analysis that require large sample databases. So when we're talking about large sample databases, that's require lots of work, either field work, analytical work in the laboratory. So it's time consuming, laborious, also require a lot of resources. So that's are the cons of the statistical analysis. Okay, and if stated here, the cons is require large database, sophisticated statistics. Example like PCA, clustering analysis, and multivariate analysis. These are not the only, not limited. This is example of the statistical analysis that's popular to identify the point source. But in much recent years, from Miller 2019, okay, we found that Miller lists 4 types of analysis that to identify source of trace metal contamination to aquatic habitats. The first one is analysis of the river alluvial stratigraphy architecture. In general, this one is identifying where the potential sediment particle, soil particle will be reside or deposited, as well can help us understand runoff that can transport one contaminants to another area during a rain event, during precipitation. Okay, another one is the relationship between geochemically defined alluvial deposit and possible human trace metal source across time. So this one, in short, we're talking about dating the elements, okay, so that we can know the history of the area, the history of exposure using that dating technique. However, when talking about dating techniques, that elements usually including radionuclide or radioactive. So it's a bit hazard to the one who operator or the one who researcher or the one who handle the sample or analyze, conducting the analytical work. Number 3 is analysis of the spatial variation in selected geochemical parameter. Okay, this one requires spatial variations, okay, of geochemical parameter, and this consume a lot of sample, lot of sampling sites. Yeah, okay, so it's again time consuming, laborious, and lots of resources needed. And the last one, number 4, is quantitative estimation of trace metal contribution from identified natural and human resources using geochemical and isotopic tracer. So I will be focusing on the isotopic tracer, as also highlighted by Miller 2019. When talking about the isotopic tracer, okay, I'm focusing with stable isotope, not the radioactive or radioisotope. Yeah, and the why stable isotope? So let's focus with the most true information, the last information at the right side. Most relevant to the isotopic fingerprinting is based on the ratio of stable isotopes. This method is more in-depth method used to identify the origin of various contamination. Yeah, and if we go back to this slide, if you notice, there's not just single elements. We have here is the slide is lead with different isotope 206/207, zinc to 66. We have copper. Okay, and this value, the ratio value, is uniquely or a signature for a different anthropogenic source. Like example, from this industry, we have the isotope ratio of lead 206/207 is less than 119. From the vehicle, gasoline exhaust, it's zinc, stable isotope of zinc with the value minus 0.18 to minus 0.58. Tires, non-exhaust from vehicle, zinc 66 with the value of 0.0 plus 0.22. So these are the example of the stable isotope that used or already established to be identification of the source of the contaminants. But I'm directing everyone's attention to the lead only. The reason why I choose lead here, let's focus with the two statements at the right side here, because it is already wide application for environmental use. It's like isotope has been well used for research in the field of geology, archaeology, and environmental forensics. Another one, by the extent used to pinpoint the source of lead poisoning based on comparing the lead isotope ratio of sample with those of possible sources, such as from coal combustion, mining, industrial emission, vehicle exhaust. Okay, because it's already widely applied for dating, yeah, for in archaeology. That is the reason why it has reference as available data to be a reference, because for a standard reference material, okay, not for the calibration purpose, but standard reference material to be referred, okay, either the data is similar or not. Okay, not many elements already established, limited. What we already available is like a carbon 13, some nitrogen 15. That's widely applied for food web trophic level. But for this heavy metal, lead is much more convenient because of the already wide application of this, and so lots of information as a reference for this element. Okay, and for the lead, it already have 4 isotopes. Okay, it has 4 isotopes, stable isotopes. I mean, 204, 206, 207, and 208. Yeah, and these three, 206 until 208, is actually an end product of uranium to thorium decay chain. You can see at the figure here, to uranium 238, and the end product is lead 206, while for thorium 232, the end product is lead 208, and uranium 235, the end product is lead 207. Okay, and knowledge about their abundance is very important. Why? Because how we express the information, how we write the data, is by the ratio. So to get the ratio, what is the denominator, what is the numerator? So it's depending on the heavy and lighter of the isotopes. So heavy isotope is the numerator, while light isotope is the denominator. So for the stable isotope lead, okay, only 3 fit for this category. 204 is not fit because it's very, very trace, 1.4. So for this 206, 207, okay, 207 is most abundant, and usually the most abundant is most lighter. So 206 and 288 is much heavier. So 206, okay, over 207, or 208 over 207. Okay, and these stable isotopes of lead is actually already established as stable most of the time, even though undergo environmental processing, okay, as well of other chemical processing or industrial processing. It will just maintain with the ratio between these stable isotopes. Now, application of these lead isotopes as pollution source tracer is actually it's already widely applied, widely applied, but not that intensive yet. Okay, the ones that we have here, 3 examples, but it's more. However, we're talking about lead isotopes. Yeah, so we have 3 here, and one from Malaysia with the title of the study, Preliminary Evaluation of Heavy Metal Contamination and Source Identification in Kuala Lumpur Smart Stormwater Pond Sediment using lead isotopic signature. And how the data is applied is by get the ratio between 206 over 207, okay, and 208 over 207, and plots in a graph, compare their reading with the reading for source related materials. Or these source related materials, example here from anthropogenic source, coal in Indonesia, coal in Shanghai, coal in Beijing, vehicle exhaust, aerosol in Singapore. This one that's already established. Okay, we can just take and refer. Industrial emission in France, or natural background source, volcanic rock in Foshan, granite in Pearl River Delta, and so on. So from the comparison we plot in a graph, you can see that the samples that from Malaysia is actually at the same, can we say like same group? Okay, they are have the similar characteristic with this data from the yellow spots, meaning that there are related material, identified related material. And when we check back, they are from coal in Indonesia, coal in Shanghai, and granite in Pearl River Delta, and uncontaminated soil in Pearl River Delta. And when we check a little bit more critical on the information of coal in from Indonesia, either Malaysia already Malaysia legally importing this coal. Yes, we found the facts that Malaysia import coal from Indonesia for our energy source. And for the volcanic natural background source, okay, even though our findings here, the data here, almost similar characteristic with this natural background from foreign country here, but since it is not relevant, okay, so we are still come up with a conclusion. The coal combustion related emissions are the dominant source of anthropogenic lead in the sediment of this pond, okay, and no significant source of vehicle exhaust and urban aerosol. So one is in agreement with the facts that Malaysia already banned leaded gasoline in Malaysia in 2000, in the year 2000. So this is in line with the facts about there's no more leaded gasoline in Malaysia. So this example application of the stable isotope of lead in identifying the source of contaminants in our environment. So that will be the end of my presentation. Thank you very much. I hope everyone can get some knowledge from this presentation session. Thank you.
Thank you very much, Dr. Firdaus. I have one quick question to you. In what way your radioisotope technique on using lead will be useful in our OTEC project? Yeah? Anyway, before you respond to that, now I think this is the end of our presentations. So I think according to the program, I think we still have time to first, I would like to revisit those questions and responses given to number of questions that have been raised earlier. And I would like to take this opportunity to give those who have raised question and whether you are satisfied with the responses given by every other speaker or speakers. If not, I give this floor to Dr. Firdaus. Could you enlighten me at least and others in what way your this radioisotope technique using lead linked to our OTEC project? Dr. Firdaus?
Thank you for the question.
Yeah.
To answer that, well, in my presentation, I didn't mention how actually the lead isotope can relate identifying the other heavy metal, okay, from the study is actually originating from the same source. So I did include in the slide, but I didn't say it out, okay. It's the correlation analysis show that other elements have strong positive relationship with the lead level. So those heavy metal is actually also included in the source of the lead for that particular pond. So the same situation is expected happen for the coastal environment, especially in Port Dickson. So now we have heavy metal data. However, the heavy metal data is not yet presented or published, so I didn't include in my presentation. Based on the heavy metal data, we find some trend that we need to further study from where actually the pollution at this Negeri Sembilan, or I mean like from Port Dickson, Lukut to Tanjung Tuan.
Okay, very clear. So basically you want to establish the baseline, because we want to draw the water from the PD for our OTEC plant. So I think good to establish such a baseline and where the sources of pollution, especially heavy metals, as you said, coming to the area. Okay, very clear. Thank you, Dr. Firdaus. So
thank you for the opportunity, Dato'.
Yeah, thank you. Very interesting. These radioisotope techniques always been my favorite technique, especially in forensic science, to trace, to differentiate different elements in the environment. I still remember this very famous the death of the blue babies, the blue baby death in Illinois, how they differentiate the sources of nitrogen, no nitrate, whether natural sources or due to the fertilizer. So that's very, to me, that's very enlightened discovery. Okay, so looking at the program, can I invite now this, is that Professor Yasuki Kigami for the closing? Professor Yasu? Yes.
Thank
Now,
you very much.
now the floor is yours,
Yeah.
right?
Yeah. On behalf of our SATREPS group, so I would like to appreciate all presenters, especially is as a keynote lecture, Dr. Satya is very, very excellent presentation. So I'm very happy to the over 70 participants. So very, very many participants hearing our activities. So this SATREPS forum is very important to understanding, to promoting implementation in Malaysia. So every March we want to hold this SATREPS forum. So next year we expected more advanced achievement. So let's join to promote implementation Malaysia OTEC. Thank you for attention.
Yeah, thank you very much, Professor Yasuyuki Kugami. And I think any participant, if you like to pursue any question to any one of us, please do drop a line or even send a WhatsApp. I'll be more than happy to share our project, in particular SATREPS OTEC project, and of course OTEC development in Malaysia. And here I would like to take the opportunity to share that we have a number of companies, including listed companies, are now very busy now looking at the numbers, and hopefully we can get the first OTEC project off, not the ground, but off the waters in Sabah and of course part of Sarawak. So we're looking forward to see you again in the meantime throughout the year. And also we are looking forward to see you again by next year. We're going to organize, as announced by Professor Yasu, the third forum of SATREPS OTEC project. So on behalf of both our Institute of Ocean Energy, Saga University, as well as UTM, Ocean Thermal Energy Center, and UTM in general, would like to thank, first of all the speakers, panelists, all the participants for having spent your time in valuable time to attend our forum. Thank you very much. All the best. Stay safe, stay healthy, and we're looking forward to see you. And this ocean thermal energy is one of the fast, I would say, the most impactful emerging technology in this 21st century. Looking forward to a sustainable future to one and all. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you.
Arigatou gozaimasu.
Abu-san, arigatou gozaimasu. Abu-san, you can keep the seat. Later, I would like to talk to you.
Yeah, sir, certainly. I want to talk to you also. Yep. We'll
Okay.
we stick around for a while. Yeah, right.
Shall we take a photo with the panelists? Don't leave, please.
Yes, can we
Panelist
stop to take a
photo.
photo for the whole group
Yeah.
as well as the panelists? Yeah, right. Sorry, I should have announced for everyone to stay
Dato',
back.
we are
for-
unable to get the
panelists.
only panelists. We are unable to get the attendees. I think so.
Okay, the panelists. Yeah. Dr. Chun, yeah, your presentation.
Professor Yasunaga? Yeah.
Yeah, Yasunaga. Okay, right. Is Kimiko there? Okay, yeah, right.